Hi y'all, it's Sarah. So today we are going to be continuing our limits portion of this calculus series with trig limits and the squeeze theorem. So first of all, here's just the definition of the squeeze theorem. So basically, the function that we're trying to find the limit of is this function g of x, right? If we can squeeze it between two other functions, f and h, near a, and these functions each have the same limit at a, then we can say that the limit of g at a is L, the same limit as the other two, right? And this might be kind of hard to understand in terms of the definition, so I'm going to draw a picture. So say that this is our function g of x, and we want to find its limit here. And we can't see what it would be. We can't figure it out with any of the methods we know. So basically, if we have a function below called f of x, and a function above, here I'll draw more like this, called h of x, that both have this limit at that point, right? Say this is a. Then we know that g of x is kind of squeezed between the two, so it must have that limit as well. So that's our definition of the squeeze theorem. And then we're going to go ahead and do an example or two. So first of all, the identity that you're going to use a lot with sine and cosine ones is this, right? And it's the same for sine. And so it turns out that it doesn't matter what you plug into cosine, right? This is still true. And so what we want to do is we want to work from this identity to get the middle part to look like the function we're trying to take the limit of. So here, we're just one step away. We just are missing the x squared. So let's multiply by x squared. Okay, and now let's take the limit of the whole inequality as x approaches 0. All right, the limit as x approaches 0 of negative x squared, we can just plug in 0 there, and it's clear that this limit is 0. Over here, same thing. We plug in 0, and we just get that this limit is 0. And because this limit has to be greater than or equal to 0 and less than or equal to 0, that means it has to be equal to 0. All right, so that's our first example. And then here's a similar one, but with sine. So we know that the sine of x is going to be sandwiched between -1 and 1. Turns out that whatever we put in the parentheses for the sine doesn't matter. This equations or inequality stays the same. And so now we just need to multiply by x cubed, and then our middle part looks how we want it to. All right, and now we take the limit as x approaches 0. All right, so plugging in 0 here, -0 cubed, we get 0. 0 cubed, we get 0. And so this, because it's sandwiched between the two, has to be equal to 0. Okay, now we're going to move on to something a little bit more complicated, but proving this is going to be the basis of knowing a certain identity so that you never have to prove it again. And so basically for this one, instead of sandwiching sine or cosine between -1 and 1, we're sandwiching x between sine and tangent. And so what we are going to want to do here is manipulate this so that we get sine x over x in the middle. So the first thing that we're going to do is take the reciprocal of everything. So we have 1 over sine x, and then the less than or equal to sign becomes a greater than or equal to sign. And then 1 over tangent of x. And I'm going to go ahead and rewrite tangent as sine over cosine. So 1 over tangent, which is cotangent, is cosine over sine, okay? Now, we have a 1 over x in the middle. We want sine of x over x, so we're going to multiply each part of the inequality by sine of x. So we have sine of x, sorry, my puppy's crying in the background, sine of x over sine of x greater than or equal to sine of x over x greater than or equal to sine x cosine x over sine x. So these cancel. We get 1 is greater than or equal to sine of x over x is greater than or equal to cosine of x. And now we want to take the limit as x approaches 0 of each of these. Okay, so limit as x approaches 0 of 1 is just going to be 1 because it's a constant. Limit as x approaches 0 of cosine, well, we just plug 0 into cosine. Cosine of 0 is 1. So the limit in the middle is sandwiched between 1 and 1, so that limit must be equal to 1. So normally when you have problems involving this, you can just use this fact as an identity. In fact, it's true for sine of x over x over sine of x, tangent x over x, and x over tangent of x. The limit as x approaches 0 of each of those is going to be equal to 1 every time. So that allows us to do problems like this example. So what we're going to do here is we're going to separate this out into the limit as x approaches 0 of tangent of 3x over x times the limit as x approaches 0 of tangent of 5x over x. Now, in order to apply this identity, we need what's in the parentheses here to be the same on the bottom, right? So if we have a 3x in the parentheses, we need a 3x on bottom. So we're going to multiply the first fraction by 3 over 3 and the second fraction by 5 over 5 in order to get those to match. I'm going to go ahead and leave the 3 from the top outside. Now, we have the same thing in the parentheses as on the bottom on both of these, and so we can apply our property from up here. And so what we're going to do is just sub those out for 1. So now we just have 3 times 5, which is 15. And so that's our limit. So you're going to have problems like these where if you can just recognize that you're able to break it up like this and apply one of these identities, you can skip the whole squeeze theorem part because, you know, this can be a little bit tedious to do with bigger problems. Yeah, so if you enjoyed this video, please like and subscribe.